Okay, welcome back to the next plenary talk. So it's a great pleasure for me to introduce Thomas Vidick. Thomas obtained his PhD in computer science in Berkeley in 2011 under the supervision of Umesh Vazirani. And then he moved to MIT as a postdoctoral researcher until he joined Caltech in 2014, first as an assistant professor, and then he was promoted to associate professor and then to full professor. Among his main awards, let me highlight a Presidential Early Career Award obtained in 2019 and an INRIA International Chair for the period 2020-2025 that he's enjoying now. Okay, he's responsible for some of the most groundbreaking contribution in quantum information theory in the last decade. And let me just mention a couple of them as an illustration. For instance, together with Umesh Vazirani, he was able to give the first security proof for quantum key distribution in the realistic scenario in which one cannot trust the quantum devices used in the protocol. And it was really a major achievement. And for instance, in a totally different direction, he also obtained for the first time a polynomial time algorithm to approximate the ground state of any one-dimensional gapped Hamiltonian, which, essentially finished a long series of numerics and analytics works. Today, he will talk about one of his most recent breakthroughs, which is this MIP star equal RE, which in a very unexpected way solves two major open problems, Tsirelson's problem and con-embedding problem that have been open for many years. And on top of all that, Thomas is a fantastic speaker, as we will have the pleasure to enjoy today. So Thomas, the stage is yours.
Oh, it's okay.
And I give you this medal.
Thanks, David. Okay, thank you very much. Thanks. Sound is okay, right? It sounds okay from here. Okay, so thanks a lot, David, for the very generous introduction. And thanks to the organizers for giving me the opportunity to speak, and to all of you for attending the talk. So it's my first time at ICMP. As David made clear, I'm a computer scientist. But the reason I'm here is to tell you about, oops, okay, so this is very sensitive, about a problem this referred to as Tsirelson's problem, which is a problem in the foundations of quantum mechanics and the definition of locality and non-locality in quantum mechanics. And the resolution of this problem that we obtained last year with my collaborators. So this is joint work with Zhengfeng Ji, Anand Natarayan, who I apologize, this is not updated. Anand is now at MIT. John Wright, who's at Austin, and Henry Ewan, who's at Columbia, and I'm still at Caltech. So the goal for the talk is, so I mean this to be kind of more of an introductory overview talk, because I don't assume that any of you are too much experts in quantum complexity theory, which is my area of research. So there won't be that much in the talk for the experts, but I hope that there'll be something interesting for the others, which is a definition of the problem, some ideas of why it's an interesting problem, why it's important, and finally some ideas of the resolution of the problem, which goes through a connection with complexity theory. So I thought it would be this thing vibrates. I thought it would be fitting to dedicate the talk to Tsirelson. So this is a picture from his student years, and this is a picture taken from his former faculty profile at Tel Aviv University. So unfortunately, Tsirelson passed away slightly over a year ago, so January of last year. So I thought it would be good to dedicate the talk to his memory. And the last picture is just to show you where I'm coming from. So this is a diagram of complexity classes, and I'll get to this right at the end of the talk. But I want to start slowly by giving a little bit of background. So going back 100 years, or almost 100 years, here is a somewhat random sample of things happening throughout the world in the 20s. So in the US, people are having fun. In Europe, we're of course more serious and having conferences and debating physics already at the time. Okay, in the US, they're again having fun, and in Europe, we're again having conferences. Okay, less fun, stock market crashes, some more conferences going on. EPR paper. And maybe the last fact is slightly less well known to this audience. It's the discovery by Alan Turing, a computer scientist, of a formal model, the Turing machine, that is meant to capture everything that is computable in principle by a mechanistic process. So Turing invented this abstraction of the Turing machine, showed that anything that, or argued, let's say, that anything that can be computed by any mechanical process can also be computed by a Turing machine. And relevant for this talk, I'll get to it much later, Turing also showed that there exist functions that cannot be computed by a Turing machine. And so these functions are called uncomputable functions, and they're going to be relevant later on. We're going to encounter one such function coming from quantum mechanics or quantum information. Okay, so I highlighted, so you can ignore everything that's in black, but pay attention to the three orangey items. These are the development of matrix mechanics by Heisenberg, the EPR paper, and Turing's discovery. So let's fast forward to the present and look at what happened to these three items. So of course, matrix mechanics has developed into arguably what is now operator algebra through the works of many mathematicians, von Neumann, and then his successors. So this is a huge area of study in mathematics, in and for itself, even separately from quantum mechanics. The EPR paper, well, there was a lot of debate following that paper, and there is still, of course, a lot of important arguments going on in the foundations of quantum mechanics, but I would kind of argue that at least in terms of volume, these arguments take less space nowadays. Quantum information has gone in a different direction, which is to ask, well, okay, what kind of things can you do using quantum mechanics? So can you do quantum algorithms? Can you do quantum cryptography? Can you do quantum communication? And this now is a huge field which didn't exist at all in the 30s, which is giving us other ways to look at quantum mechanics. And finally, computing devices. Well, I'm a computer scientist, so I'll say that these have exploded. Of course, everyone here has a cell phone and a computer. But it's not only for these practical constructions. Also, this abstraction of the Turing machine has led to theoretical computer science, which is really a field of theoretical research, which has its own theoretical results that are closer to maybe discrete mathematics. And there's a big body of work that this talk is going to draw on. So these are the three threads that are going to come together in the talk in this order. So I'll start by quantum information and sort of stating Tsirelson's problem, kind of in the way that he stated it himself. Then I'll give you a sort of very high-level explanation of the connection between Tsirelson's problem and some foundational questions in operator algebras, so namely Kahn's embedding problem and the work of Kirchberg. And then in the last part of the talk, I'll try to give you ideas how complexity theory of computation gives an answer to that question in the foundations of quantum mechanics. Okay, so to start, I just need to maybe remind you very quickly, a review what is quantum entanglement and what do we mean by non-locality. So I think maybe everyone here knows this, but let me just say it really quickly. For me, for the purposes of the talk, entanglement is a state of matter. So it's a physical state that a certain number of particles can be in, which has certain properties. And the property that we're interested in is the fact that if you take two collections of particles that are in an entangled state and you make local measurements on these particles, then the outcome statistics of these measurements can be correlated in particularly strong ways, stronger than the kind of correlations that you'd get if you tried to model the whole setup using classical Newtonian mechanics. And we're going to make this precise on the next slide. I just wanted to give you the time if you want to read the definition from Wikipedia, which I find reasonably accurate as a first definition of what the phenomenon is. All right. So these correlations, we kind of need a framework in order to express what they are. So in what sense do we mean that quantum mechanics is non-local? So I'm going to describe on this slide the precise sense that was given by John Bell in the 1960s and his collaborators. So John Bell looked at the problem of entanglement with great clarity that's, I mean, I wouldn't blame them, but that's definitely not present in the EPR paper. So he formulated the setup in the following way. So let's imagine that we have two physical systems. So here I drew them as a photon and a photon, but they could be larger systems, could be more photons, or could be atoms. The point is just that this should be a non-relativistic quantum system. And let's imagine that on each of these systems, we can make a certain number of measurements. So these measurements are parameterized by a variable x. So this could be a position measurement. It could be an angular momentum measurement. It could be a spin measurement, depending on what kind of system you have. And each of the measurements you can make can produce certain outcomes. So spin up, spin down, certain position, things like this. So I label outcomes as A. The other system, you can make other measurements labeled by Y, and they produce outcomes by B. So if you imagine preparing identically your physical system many times and making all possible measurements and collecting the statistics, the description, what you can observe from this experiment is a collection of probability distributions. Okay? For every pair of inputs, there's a certain distribution of outputs that this system produces when I make the measurements that are labeled X and Y. And so now the question is, well, depending on our physical theory, how we decide to model this system, different kinds of families of probability distributions are permissible. So I'm not going to insist too much on the classical model because it's less relevant for the talk, but just for intuition, this is maybe if you didn't know about quantum mechanics and you knew about Newtonian mechanics, this is maybe the simplest thing that you'd come up with. You'd say, well, look, okay, so each physical system has its own local behavior. So on the left, we have probability distribution, Q of A given X. On the right, we have a probability distribution, Q, I think, can I? Okay, I'm not going to try to point to I think it's possible, but QB of B given Y. And then there's a classical random variable lambda here that has its own distribution that might correlate the two systems together. So think of lambda as some kind of history that describes how the systems interacted in the past. There's some shared information between them. So I took a mixture or convex combination over all lambdas. Okay, so that's what I'll call the classical model. And Bell's discovery is that there exist some distributions that have a model, some families of distributions like this that have a model in quantum mechanics, but that do not look like this. So do not have a representation as a convex combination of product distributions. And this is what we call the non-locality of quantum mechanics, that it allows such kinds of distributions to be generated. So now comes in Tsirelson. So about 2 decades after Bell's work, Tsirelson was trying to understand, okay, well, fine. So Bell and others showed us that there exists distributions that can be generated by quantum systems that don't have a model of this form. So let's try to understand the extent of these quantum distributions. How do we model them mathematically, and what are their limits? Before his work, I think the only limit that people wished was there is that there shouldn't be any causal influence between the input of one system to the output of the other system. But even verifying that requires you to set up the problem precisely. Tsirelson is famous for multiple things, but one of the things that he's famous for is something called Tsirelson's bound, which is an analog of Bell's bound, or the Bell inequalities, but it's a bound that limits the non-locality of quantum correlations. It's more than a bound, it's a set of techniques that can be used in order to bound the strength of quantum correlations and separate them from, in principle possible, but it seems not physically reasonable kinds of correlations, such as non-signaling correlations, which I'm not going to get into. Okay, so let me describe a little bit more precisely the framework that Tsirelson introduced to model these correlations. So this is maybe the important slide in terms of notation. I hope everyone can follow what's going to be written here. I'm sorry, this should be shifted to the left. So in the slide, we're trying to understand what kind of mathematical representation can we give for the kinds of correlations that can be generated in quantum mechanics. And Tsirelson came up with 2 different models. So the first is called the quantum spatial model. So this is not his terminology, but it's terminology that arose later. So in that model, we say that to each particle should be associated a Hilbert space. This Hilbert space could be finite dimensional, or it could be infinite dimensional separable. And then there's a quantum state, which here I represent as a unit vector that lies in the tensor product of these 2 spaces. And so now how do we model measurements that can be performed at each system? So the system on the left, there's a collection of positive operator valued measures. So this is a set of positive semi-definite operators, P, X, A. So they're labeled, they're indexed by the different measurements that you can make and the outcomes that you can obtain. And so these should be partitions of unity. So they should sum to the identity for every possible X. And they act on the first Hilbert space. So similarly, for the other system, we have a family of measurements Q that acts on the Hilbert space that's associated to the second system. And if you set things up in this way, then the Born rule, the measurement rule for quantum mechanics, says that if this is your physical setup, then the probability of obtaining outcomes A and B when you make measurements X and Y, X on the left, Y on the right, is given by this overlap here. So bra psi, P tensor Q, ket psi. So that's maybe the most standard model, at least in quantum information. It's really the standard model for locality. You have a Hilbert space associated with each particle or each subsystem, and you take the tensor product of the Hilbert spaces to get the Hilbert space of the total system. But you could be a little bit more liberal and say that, look, this tensor product is kind of a fabrication. Let's just have a single Hilbert space for the whole system. And we have measurement operators, P and Q, the same as before, except all of them act on the same Hilbert space. Now, by Born rule, you can see P is multiplied by Q because they act on the same space. But still, I kind of want to enforce some minimal requirement that expresses locality. In particular, there should not be causal influence between the two systems. So it shouldn't matter in what order these measurements are performed. And one way to enforce that is to require that the measurement operators should commute. So here, the commutation rule is between any P and any Q. Okay, different P's don't need to commute, but P's and Q's always commute. So this is fittingly referred to as the commuting model. So Tsirelson introduced these two models, and then in a paper in 1983, I think, and then he went on to say, well, these two models are equivalent, so let's work with the first one because it's more convenient. Tensor product gives you a little bit more leverage. Maybe we can observe already that the second model is more general because if for the purple part, the Hilbert space happens to be a tensor product, and P's happen to act on the left and Q's on the right, then of course they satisfy the commutation condition, okay? So Tsirelson went on and he worked, all of his results are proved in the tensor product model, and later researchers in quantum information asked him for a proof, but then he realized that he does not have a proof that the two models are equivalent, and so he formulated it as a problem, as an open problem. And so this is, in Tsirelson's words, this appeared on his webpage. This is a formulation of Tsirelson's problem. So are the two models that were described on the previous slide that I'll give you again a little bit later, are these two models equivalent? Or conversely, are they not equivalent, which would mean that there exists families of distributions that can be that have a model in the more permissive one, the commuting model, but not in the tensor product model. So let's talk a little bit more about this problem. I'll give you different perspectives on it. Here's a geometric perspective. So I can introduce two sets. So maybe let me draw this. Both of these sets, C sub QS and C sub QC, are convex sets. They're subsets of 0, 1 to the n squared k squared. So what's n and k? These are the number of measurements that you could make on each system and the number of outcomes that each measurement returns. So I'm only thinking about finite numbers of measurements, finite number of outcomes, and for simplicity, we just assume that the number of outcomes is the same across all possible measurements. So think of n and k as small parameters. So this problem tends to have very specific behavior if n and k are equal to 2. But as soon as you allow at least one of them to equal 3, or let's say both of them to equal 3, then the problem becomes essentially as interesting as the general case. So think of n and k as, let's say, 5 for safety. OK, so what are these sets? So each point in my square is a family of distributions. So it's all these coefficients, p of ab given xy, for ab ranging between 1 and k, and xy ranging between 1 and n. So I want to draw two sets. The first is all these points that have a model in the tensor product setting. So you can see up there, I wrote the definitions again, and then the other set is, in principle, could be bigger. Tsirelson's question is whether these two sets are equal or if there's a difference between them. I want to point out right away, just in case it confuses anyone, that there's kind of like two intrinsic notions of dimension that can be associated to this problem. So one is the dimension that's implicit in the parameters n and k. And this one is less important for us. As I said, n and k can be thought of being 5, 6, some small numbers. And then there's another dimension, which is the dimension of the Hilbert spaces that are used to represent these points. So each point in my figure is a point that has, let's say, 5, so it's 25 times 25 coordinates, so it's a vector of finite dimension. But if it's in the purple set, for example, that vector has a representation using positive semi-definite operators and a state in a certain Hilbert space. That Hilbert space might require a very large dimension. In fact, it could be infinite. Okay, so in principle, and in fact this is the case, there can be points in the purple set that require infinite dimensional Hilbert spaces in order to identify a representation for them. Okay. Okay, so what's known about this? First thing, this is easy to check. Both sets are convex. You can see that by taking direct sums of all the objects that appear. This we already observed, that one of the sets is included in the other. A slightly harder exercise, but this is what maybe misled Tsirelson, is that if you restrict the dimension of the Hilbert spaces in both CQS and CQA, then the two sets are equal. So you can show that in finite dimension, if you have two collections of operators and they mutually commute, then in fact you can write them as tensor products. Okay, but if you allow the dimension to be arbitrary, then a priori we don't know. Something much less trivial that I'll get back to in a slide or two is that okay, the purple set CQC is closed. This is not hard. But the blue set turns out to not be closed. This is a hard result. I'll get to it soon. So here's a reformulation of Tsirelson's problem, because one set is closed and the other is not, and of course they're different. But let's take the closure of the blue set and then ask. So the closure now is in this. It's a very simple closure. It's in this finite dimensional Euclidean space. If the closure of the blue set is equal to the purple set, and so that's mathematically formulated. This is Tsirelson's problem. So this is the problem that we want to think about. Let me say a little bit more about related questions. So there's in fact many of these sets that you can introduce. Here is a selection of them. I didn't draw them on the picture because there's too many, but a well-studied one is the classical set. So this would be a convex subset of the two sets I drew before that represents all these families of distributions that can be achieved in classical mechanics. So the model that I had a couple of slides ago. CQ would be the same as CQS, except you restrict the Hilbert space to be finite dimensional. CQS we encountered before. CQA is the closure of CQS, and CQC is the commuting set. So what's known about these? So the work of Bell was to separate classical from quantum correlations. So he separated these two sets, CC and CQ. The result that I mentioned on the previous slide showing that CQS is not closed. So let me say a word about this because it makes a very nice connection that hints at why this problem is a rich problem mathematically. So what Sloftra did is connect the problem to group theory. So he proved something that's called that he calls a universal embedding theorem. So this theorem allows you to start from any finitely presented group. So finitely many generators, finitely many relations, but the group could be infinite. And from this group, he constructs parameters n and k that depend on the presentation of the group, and a linear function in R n squared k squared. So a linear function that acts on the space of correlations, such that the following properties hold. First of all, there's a normalization condition. The supremum of this linear function on the commuting set is 1. That's just normalization. Then the two important conditions are as follows. So I forgot to say this, but it's written on the slide. So the linear function depends on the choice of an element in the group, W. You just choose that. You choose it by a representation as a product of generators. And then there's some automatic procedure for computing this functional. And it'll have the following two properties. First of all, is if the element, your group element, is non-trivial in approximate finite dimensional representations. I'm not making this precise, but these are not necessarily representations, but they're things that approximately respect the group, their functions from the group to unitaries that approximately respect the group multiplication law. Then, in fact, this linear function will achieve its supremum in the closure of the quantum set. And if, moreover, the element that you chose happens to be non-trivial in exact finite dimensional representations, then the supremum of this linear function is in fact achieved in the quantum spatial set itself, not its closure. So I'm not going too much into details here, but for people who study group theory, then they can see that now the only thing that you're missing is a finitely presented group that happens to be hyperlinear, so that the first condition is always satisfied, but not residually finite dimensional, so that there's an element such as the other condition is not satisfied. And groups that are hyperlinear but not residually finite dimensional, this is easy. People know such examples. And then you apply the theorem and you conclude that the quantum set is not closed because you'll have a linear function that achieves its supremum on the closure of the set but not on the set itself. And for this to happen, of course, it cannot be closed. Okay? He even obtained a stronger result, incomparable result, which is a computability result that relies on the fact that the word problem is undecidable. But let me not get into that. The reason I put this is more to emphasize that a very important point in the analysis of these correlations is that certain correlations, for example, correlations that achieve the supremum of this linear functional here, can only be achieved in Hilbert spaces that support measurement operators that satisfy very specific algebraic relations. Here, if you look at the proof is going to require certain correlations, the measurements that realize them, to satisfy the group relations. And this is how the group comes from the correlation. This is very surprising because a correlation at first is just a collection of probability distributions. There is no algebraic structure. But the point is that certain correlations force a specific algebraic structure, like multiplication rules, on the operators that realize this correlation. And that's really the source of why this problem is so rich. Okay, and finally, this is more elementary but very elegant proof, shows that the finite dimensional and infinite dimensional sets are separated. So this is to say that prior to our work, all these separations exist, and we're focusing on the last remaining one. Why focus on this one? Well, because the others are solved, and also because I think it's maybe the second most interesting one after the one that Bell solved. I mean, this is really the most interesting thing, separating classical for quantum. So it's interesting for fundamental reasons, and also interesting because of the connections to operator algebras that I'm going to review now, and then we'll go into the proof of the separation, so the one that's missing in the slide. Okay, so this is kind of self-contained. So if you're not interested in the operator algebras, you can blank out for 3 slides, but it's going to remain high level. So operator algebras, the field was born from the efforts by von Neumann and Murray of formalizing the notion of von Neumann algebra and then classifying von Neumann algebra. If I say some words, I thought I should put the definition. So if you care, this is a definition of von Neumann algebra, but it's not really important. So these von Neumann algebras come in different types, or at least the factors come in different types, depending type 1, 2, 3, depending on the kinds of depending on the kind of projections that they contain. So Murray and von Neumann classified type 1 von Neumann algebras. These are kind of like the finite dimensional von Neumann algebras. They also studied type 2 factors. Later in the 70s, Alan Kohns worked on the classification of type 3 factors, and he received the Fields Medal for his work towards the classification of type 3 factors. In the process of classifying type 3 factors, he writes, this is more like an offhand comment in his famous paper, classifying type 3 factors. In the paper, he meets a type 2 factor called n that I'm not describing. But he shows that this type 2 factor has an embedding into a particularly nice factor. So, and again, I'm not giving you the definition. R is called the hyperfinite factor. It's like an infinite tensor product of many copies of M2, 2 by 2 matrices, but and then he poses what is now known as Kahn's embedding problem, which is that every type 2 factor would have an embedding into this hyperfinite factor. So it's a bit hard to digest if you don't know von Neumann algebra. So let me give you something, a formulation that I like, that I find easier to approach, even though it's a weaker conjecture. So the following is the question of whether every finitely presented group is hyperlinear. If it's weaker than Kahn's embedding problem in the sense that Kahn's embedding problem can be false, which is what I'm going to show, but this conjecture here is still open. But qualitatively, I find it similar. So this is a question of whether if you take so the notion of a countable group being hyperlinear is that there should exist for every integer n a map from the group to unitaries. And these maps are not required to be homomorphisms, okay? They're just maps from the group to unitaries, such that for any 2 group elements, then in the limit, as you take n to the infinity, the maps multiply approximately in a suitable norm. So here, this is the Frobenius norm that's been normalized by the dimension of the unitaries. And the second condition is to require that the map is non-trivial. So here, the order of the quantifiers is important. If I said that if the limit over n was taken outside of the for all quantifier, then you'd obtain a much stricter notion. So this is a very loose notion because the speed of convergence to 0 is allowed to depend on the group elements. Okay. So this was just to give you a hint that Kahn's embedding problem is also some kind of approximation question like this of an infinite dimensional object by finite dimensional ones in the limit, but it applies to von Neumann algebras and not to groups. Okay, so why is this problem that Kahn was actually not so interested in? I think that's what he says at the time. Why did it gain so much prominence? Mostly through the work of Kirchberg, who's a famous operator algebraist, who introduced a conjecture in operator algebras, the Quebb conjecture, and he showed that this conjecture is equivalent to many, many conjectures. Here on the slide, I wrote one. This conjecture is about the equality of two different ways of closing the algebraic tensor product of two copies of the group C star algebra of the free group F2 with two generators. In fact, this is equivalent. This question is equivalent. You can have more generators. And through Kirchberg's work and the fact that it was equivalent to so many conjectures, this is when it became more interesting. So a little bit later, Fritz and Junge and collaborators, including the session chair, David Perez-Garcia, made the connection to quantum information theory and to Tsirelson's problem. They showed that if Kahn's embedding problem equivalently Kirchberg's Quebb conjecture has a positive answer, then Tsirelson's problem also has a positive answer. And if you know a little bit of tensor products and C-star algebras, you might not be surprised. It's a bit surprising coming from Kahn's embedding problem, but coming from the equivalent formulation of Quebb that I wrote on the slide, then if you know the definition of min and max tensor products, you can see where this commuting and tensor kind of correlations that I described before, where they would arise from. This was strengthened later by Ozawa, who showed that in fact there's an equivalence. So Tsirelson's problem is equivalent to Kahn's embedding problem, is equivalent to Kirchberg's Quebb conjecture, and in fact to many other conjectures, some conjectures due to Voiculescu, some reformulations due to Voiculescu in free entropy. There's some reformulations in group theory. There's some slightly weaker formulations in the theory of graph limits. Group theory I already mentioned on the previous slide. So this is a very, very rich problem. You wouldn't expect this when you start out just from the quantum mechanics. All right, so this is the end of my operator algebras aside, and now in the remaining time, like 20 minutes or something, David? Yeah. I'll try to give you some ideas of how we go about proving a negative resolution, so separating these two convex sets, so that's going to be the main result. The closure is strictly included in the QC for some n and k. So I'm not going to say what this n and k are. Earlier I said you can focus on 5. I wish I could prove this for n and k equals 5, but in fact they're much bigger, but you could extract them from the proof. The proof is explicit in the sense that if I wanted, I could give you a printout of these, what n and k are and what these correlations are. Okay, so here's the surprising fact is that we're going to show something stronger. We're going to show a complexity theoretic result. We're going to show that the problem of optimizing linear functions over the convex set CQS is a problem that's intractable. If you know a little bit of optimization, that's surprising because optimization of linear functions over convex sets, that's supposed to be the easiest thing in the world. But it's easy if you have a membership oracle, in case you know optimization. And here, the point is that we're not going to have a membership oracle. We're going to show that implementing a membership oracle is this is an undecidable problem. So this is, as far as we know, stronger. You don't need to show this in order to separate the two sets. But if you show it, then you can conclude that the two sets are separated by some earlier works that I'm going to mention. All right. So now I'm going back to sort of basics, back to the start. So this is the same picture that we had before. I'm studying two convex sets. If you remember the definitions, CQS is the set of families of distributions that have a model in quantum mechanics when you force local systems to be in tensor product form. And CQC is the set of families of distributions that have a model in the slightly more general commuting set, where there's a single Hilbert space and all operators act on the Hilbert space, but they're required to commute when they're in spatially isolated regions. Okay, so we have these two sets. We're trying to separate them. What's the most basic approach? Well, we're going to try to draw a linear function in our space, and we study the largest value that this linear function achieves on each of the two sets. And if we find any linear function like this, such that the supremum over the blue set is strictly less than the supremum over the purple set, then we're done, right? The sets must be different. And the supremum takes into account the closure, because when you compute the supremum, it only sees the closure of the set, not the set itself. Okay, so this is what we're going to do, and this is first main result. And as I mentioned, the way we're going to show it is by proving something a bit stronger, from which the fact that the two supremums are different will follow. We're going to show that a certain computational problem that's written here on the slide is uncomputable. So precisely, here's the computational problem. You're given as input, first of all, what n and k are. So these specify the sort of exterior dimension of the problem. And you're given a linear function on that space. And instead of putting it on R, I put it on Q so that this linear function is specified by rational coefficients, so you can represent it finitely. And you're told something, which is that this linear function, the supremum of it on the blue set is either at least 1 or at most half. Okay, so you're given like some wiggle room there. It's not like it's going to happen at the 10th digit or something. There's a different. It also should be normalized in a natural way. I didn't put that on the slide. And the question is to decide which. Okay, so this is a computational problem. It has as input a bunch of rational numbers, and the output is yes or no, or, or 1 or half, one of the two. And so what we'll show, and I'll get to right at the end of the talk, is that this problem is undecidable. So there's no algorithm in no amount of time that answers this question. It's kind of surprising, right? Because it's kind of a basic question. I mean, if you know about Bell inequalities, this is just asking, is the largest violation in quantum mechanics of this Bell inequality, lambda, at least 1 or at most half? And the result is that there's no algorithm that's going to tell that. So before going there, I want to explain in just one slide why this result in complexity or computability theory implies that the two sets are different, because at first it's not, all these things could be uncomputable and still the sets are equal. So we need a little bit more results to get there. So here are things that are known prior to our work that have been put in place by people who do experiments and actually need to compute these quantities to make predictions for their experiments. So people know that there's two algorithms that you can use if you're trying to compute the largest quantum bound, so this omega star quantity. First of all, the most naive thing you could do is perform some exhaustive search by below. You can search, right? You can take the Hilbert space to be dimension 2, you put an epsilon net over the operators, and you kind of look how well you can do it. Then you do dimension 4, you do dimension 8. It's quickly going to take a lot of time, but in principle, you can do it. So you can definitely find a family of lower approximations to the optimum over the tensor product set. And if you know a little bit of algebra, you know that this is actually going to converge. So this sequence converges from below by below to the correct value. For this, you need to know that the limit over finite dimensions will give you the infinite dimension when you're talking about this tensor model, but that's the case. It's not hard to see. Okay, so this is fact 1 that's known. Then fact B is that we also have outer approximations, so you can compute a sequence of upper bounds. And this sequence of outer bounds, this is much harder. It's obtained by constructing outer approximations to our convex sets that have representations using positive semi-definite inequalities. So this is work that's due to Navasquez, Pironio, and Assine in quantum information. It's sometimes known as the Npa hierarchy. So it's a little bit more complicated, but it is a sequence that converges. However, you can see it's important what I wrote, to be careful what I wrote here. So the sequence that converges from below converges to the optimum over the tensor product set, QS, and the sequence that converges from above converges to the optimum over the quantum commuting sets. And these are just things that are known that you can prove based on the definition. Now, suppose that the two sets are equal. Okay? Then I claim that we would have an algorithm that computes the value, and this algorithm would just interleave the two algorithms. So the reason I don't have an algorithm so far, let's say the one that goes from below, is that you know that it converges, but you never know when you're getting close. And so that doesn't give you a computable function, because you're going to compute these values, and let's say it stays stuck at a half, for a decade or something, half. You don't know if you got there, or maybe it's going to jump to 3/4 tomorrow, right? So you have to wait until tomorrow. And so that's not an algorithm. It's just because you don't know when to stop. However, if these two values are the same, then you get an algorithm, because you have an algorithm from below, an algorithm from above. You compute the two of them together, and you'll at any point be able to estimate if you're almost there or not. If I have a half and 3/4, I know I need to continue. If I have a half and half plus epsilon, then I know that I can stop. I've narrowed my gap as much as I can. So I can't predict how long it will take, but I have a stopping criterion. And so this fits the definition of a computable function. Okay, so if the two sets were equal, we could put these algorithms together, and deduce that either of these optimum is computable. And so in order to show that the two sets are different, it's sufficient to prove that either of these two values is uncomputable. And so we're going to show that the first one is uncomputable. We could have tried with the second one. Okay, so this I said already. So this was the connection between computability and separating the two sets. And so now for the remaining time, I want to try to explain to you why this is not the case. So why the quantum value in the tensor product model cannot be computed by any algorithm. And this will wrap up the whole argument. Okay, so this is what I called main result 2 earlier. Okay, so now we're getting towards the end of the talk, and I'm going to switch towards a little bit of complexity theory. So I hope you can still follow me. There's not that much that I want to show. So how do you show that a function is not computable? You do a reduction. You start from some other function that you know is not computable, and then you show that if you could compute your function, then you could compute the uncomputable function, and so you get a contradiction. So the standard uncomputable function is called the halting problem. So Turing showed that this function is uncomputable. What this function is that you're given as input a description of a Turing machine. So think of this as a description of an algorithm. It could be written in any sufficiently rich code like C or Python or whatever. And the question is, if you run this algorithm with no input at all, does it halt or not? Okay, eventually. So Turing showed that this problem is uncomputable. Basically because the only way to know if it's going to halt or not is to run it. I mean, sometimes you can stare at the code and see that it's going to halt pretty quickly, but sometimes you can't really see anything and you have to run it, and it could run for any amount of time, and so you just can't decide any faster. So Turing showed that the halting problem, this problem is uncomputable, and so our goal is to do a reduction. We want to start from this problem, whose input is a Turing machine, and we're going to try to map this Turing machine to a linear function on the space of non-local correlations, such that if the Turing machine halts, then this optimum of this linear function, which you can think of as the coefficients of a Bell inequality, if you know what Bell inequality is going to be 1. And if the Turing machine does not halt, then the optimum is going to be at most half. So this completes the argument if we can do that, right? Because if you could compute the quantum bound, so if you could distinguish between the two cases 1.5, then by following the reduction, you'd be able to decide whether this Turing machine halts or not. But Turing showed this is impossible by very simple, logically involved, but simple argument. Okay, so we have to do this, map Turing machines to Bell inequalities. So this sounds a little bit crazy, but we're going to go about it in 2 steps. And these 2 steps have been refined in quantum information and quantum computing, quantum computer science over the past 2 or 3 decades. So this is not, I'm not inventing this proof strategy here. The first step is that we're going to interpret the quantum bound as a success probability, so a number that's associated to a certain game. What kind of game? These are games that are very popular in quantum information, also quantum cryptography. There's Alice and Bob. Alice and Bob have a quantum system that they share. Each has their own particles. And then there's a referee that runs the game. Think of this referee as the experimentalist setting up the Bell violation experiment. So they choose measurement settings, but now we call them questions. And they send these questions to the Alice and Bob, the physical systems. Alice and Bob perform whatever measurement they want on their system, and then they reply with answers. And this referee is going to decide to accept or reject the answers using a publicly known criterion. The goal of the players, they know the rules of the game, and they're trying to succeed, maximize their winning probability. And the requirement is that they should be spatially isolated. So if you write things out, here is a formula for the player's maximum success probability in the game. It's the supremum over all strategies. Okay, what's a strategy? What are these players doing? How do I model them? In general, they get questions X and Y. They produce answers A and B. So I can model them using a correlation, a family of distributions, P of AB given X, Y. And depending what kind of physical restrictions I put on them, they'll be able to generate different families of distributions. So then I'm summing over all questions X and Y and answers A, B. Pi is just the probability with which these questions are asked. V is a 0-1 number, which says whether A, B are valid answers to questions X, Y, or not. And then there's the probability that these answers are given. Okay? So if you look at this, this is a linear function, okay? It's a Bell inequality. It's just that the coefficients of the linear function or the Bell inequality have a bit of a specific form. Because I'm thinking of that inequality as a game, the coefficients need to be non-negative, and then there's some kinds of normalization. So I'm restricting my attention to specific Bell inequalities, specific linear functionals. What I gain from it is this way of thinking about it. Now I can think of the maximum of the Bell inequality as a maximum success probability in a two-player game. Okay, what's the advantage of that? The advantage is that two-player games and the problem of computing maximum success probabilities in two-player games have been studied a lot in classical computer science in connection with complexity theory and the study of constraint satisfaction problems and interactive proofs. And it's through this connection that we're going to ultimately be able to show that the problem of computing this number there when over the set, so did I write over the set QS? Yeah, that problem is an uncomputable problem. So I'll just take 5 minutes to hint at how complexity theory goes about these things. So I'm going to tell you a little bit about complexity classes. So maybe this is people are familiar with. So complexity classes are just classes of problems. A problem you can think of as a list of all possible instances and then the answer to the problem. So this is something abstract. A complexity class is just a collection of problems that is classified together because they have the same difficulty of solving them. So the easiest complexity, or the most, sorry, not the easiest, the most standard complexity classes are P. But here I wrote BPP because I'm talking about probabilistic computation, but think of it as P, if you know P for polynomial time. BQP is the quantum version. And so you think of these problems are problems that can be solved in the following way. So you get an instance to the problem. For example, this is a graph, and the question is this graph connected? And then you have an algorithm that stares at the instance for an amount of time that's polynomial in the length of the instance. So if it's a graph, it would be the size of the graph. And it has to produce an answer. Okay? So we'd like all problems to be solved have an algorithm in this way, a polynomial time algorithm. But we also know or believe from complexity theory that's not the case. There are some problems. For example, the graph coloring problem. So given as input a graph, is this graph colorable? We don't have an algorithm for this. But we still want to say that it has some interesting feature. The interesting feature that the graph coloring problem has is that you can easily recognize solutions. If you have a graph and a valid coloring of it, what's a coloring of a graph? It's just colors for all the vertices such that vertices linked by an edge have different colors. Okay. If you're given such a thing, then you can recognize, you can check. You just look at the graph and you can check that it's valid. But finding it by yourself may be hard. So problems of this form, they lie in the class NP, and here I put the symbols for the probabilistic and quantum versions, MA and QMA. So these are problems such that you might not be able to decide the problem by yourself, but you can decide it if you're given help. You're given a certain proof, and then you can check the proof. So this is basics of complexity theory. It's like the 70s, and since the 70s, people have realized that there's more problems that don't fit in that class either. A nice example is the graph non-coloring problem. Okay, given a graph, is there kind of like some hint or some advice that you can give to someone that demonstrates to them that the graph is not colorable? Okay, that's hard, right? Because there's not like, what can you tell me? I mean, you can tell me, but then if I don't believe you, it's not like coloring. I can check the coloring, but non-coloring. Okay, so to study these kinds of problems, complexity theorists invented two further generalizations of these classes. The first generalization is interactive proofs. So now you broaden the model a little bit and you say, okay, it's not just that you should give me something that I can verify, but we can have an interaction. So if I'm trying to check that this graph is non-colorable, I can ask you, well, could you please show me a few colors or maybe give me all the colors, and then, well, they shouldn't exist. So you have to flip things around. I have this interaction and try to convince me that the graph is not colorable. And so in the 80s, researchers in cryptography and complexity theory showed that the graph non-coloring problem and many other problems, in fact, all problems that can be solved in polynomial space, have interactive proofs. And they continued. And the last generalization was to introduce what's called multi-prover interactive proof systems. And you can start seeing diagrams start looking a little bit similar to games. Okay? The last generalization now is to ask, well, what if I can not only get a static proof, like a coloring, but I can interact with a machine that's very powerful and is going to answer all my questions, but I might not trust it. But now what if I could interact with two such machines that can answer my questions, but I might not trust it? That could give me more leverage. Think of it like interrogating prisoners. You put them in different rooms. You get leverage over them. So this gives you a complexity class that's known as MIP for multi-prover interactive proofs. And there's a very, very famous, very important result in complexity theory in the 90s that characterizes the complexity of this class as being exponentially larger than what we started from. What we started from was NP, static verification. Now I added randomization, I added interaction, I added interaction with two parties, and I get exponentially more verification power. So this is a very important result in complexity theory. It has led to many, many follow-ups in all directions. Hardness of approximation, this result is even used in some cryptographic protocols to have efficient verification of programs, things like this. So it's, I'm not doing it justice here. But I want to end by connecting to our setup. My point here was just that you have these different models of verification, and people characterize the complexity of the problems that can be verified in different models. And now if you've studied this and you know a little bit of entanglement, then you want to say, well, OK, like how does the model change if these two provers that we're interacting with are allowed to share entanglement? So this is a representation for entanglement. This leads to a new complexity class that's introduced by Cleve, Oyetono, and Watrous in 2004. The star refers to entanglement. And they ask the question, what is the power of that class? What languages can be verified in this model? And there's a very simple connection that I'm not making formally between this question, the complexity of this class, and the question of studying the maximum acceptance probability in two-player games. Because protocols, interactive protocols in this class, you can think of them as two-player games. Okay? I again have questions that I ask my provers and answers that I get back. And these answers are given according to a certain distribution. I take the supremum over all such distributions in a certain physical model. And that will allow me to decide the maximum acceptance probability, so to decide the language. And so if you know the definitions, it's an exercise to show that if this class contains undecidable problems, then the problem that we actually care about, this quantum optimization problem, is uncomputable. And so that's what we show. We characterize this class as much bigger than the other ones. Somehow the introduction of entanglement makes the class bigger. It's equal to RE. RE is the set of all recursively enumerable languages. So a complete problem for the class is the halting problem that we encountered. So this class contains all problems that have algorithms, and also in any time, and also some problems that don't have algorithms, such as the halting problem. So how do we show this? I'm out of time now, so I'm not going to argue how do we show this. But we build on the two ingredients that I've introduced. The second, the one that I introduced at the end, is just the thinking of these Bell inequalities or two-player games as verification procedures, and playing with that, like the graph coloring and these kinds of problems, trying to find protocols for them. And the second connection is the connection that was used in Slofstar's result, but that dates to before, is using games or interactive proofs to force certain behaviors, and these behaviors in terms force algebraic relations between the measurements that realize the behavior, and then working from there. I mean, of course, there's a lot of work that I'm skipping, but you can arrive at these kinds of characterizations. OK, so I realized the end was a little bit quick for anyone who's not a complexity theorist, but I just want to give you a little bit of a flavor. Let me end now to summarize what we've seen and maybe a couple open questions. So Tsirelson's problem had to do with these two sets that I put back at the top here. For any finite n and k, you have two different sets, and the question was whether these two sets are equal, or let's say the closure of the two sets are equal, and so we showed that it's not the case. Through connections that are due to previous work, this answers some conjectures and operator algebras in the negative. And our proof goes through a slightly stronger result, which is to show that certain optimization problem is uncomputable, and then by previously known results, we obtain the separation. I think it's an interesting open problem that I'd like to see solved, which is to show the separation without using any complexity theory. And anytime I talk to someone who's not either a mathematician or a physicist, they don't want to learn about Turing machines. They just want to prove that doesn't involve Turing machines. But I'm not the one capable to do that. So I think that's an interesting open problem for some audiences. A couple other open problems. The proof is explicit in the sense that it gives you a point in the purple set, but not in the blue set, and I could print out that point. What I can't so easily print out is a model for that point. So what are the spaces and what are the commuting operators that realize that correlation? And that, depending what you mean by explicit, that might be kind of required to get a very explicit construction of a 2-1 factor of one-dimensional algebra that doesn't have the kind of embedding that Kahn's kind of thought should exist for all such algebras. Maybe a question closer to this audience has to do with QFT. So you could ask what models of quantum mechanics would allow you to differentiate between these two tensor product and commuting models. So the fact that space-time isolated regions, that this isolation is enforced by requiring that associated algebras of observables should commute. This is one of the axioms of algebraic quantum field theory. So you could imagine that in quantum field theory, you can find physical models that allow to witness the separation that here is a purely mathematical separation. I'm really not an expert, but as far as I know, every time you make your quantum field theory model slightly more concrete, you have to say what is the, what are the C-star algebras or the von Neumann, and then they always tend to have some property. An example is the split, something called the split property. And if you have that extra property, then in fact the two models are equivalent. So it's kind of hard to find concrete models in which the separation, concrete physical models that have physical sense in which the separation can be witnessed. Okay, and this I mentioned already. So I'll stop by thanking my co-authors and Boris Tsirelson for asking a great question, and the audience for staying. So thanks.
Thank you very much, Thomas, for the very nice talk. So are there questions? So I do have one. So is there any idea you have to solve this problem about hyperlinear groups?
So I said this is a weaker conjecture whether every group is hyperlinear. So now that there's a negative answer to Kahn's embedding problem, so you might think, and I think even before this is what maybe mathematicians or group theorists would think. It would be nice if every group was hyperlinear, but groups are wild, and so maybe there's some non-hyperlinear groups. So there's actually a whole framework for trying to approach that question using the ideas that are in the talk. This framework was put in place mostly by Slofstra. That framework says that if you restrict slightly further the kind of Bell inequalities or two-player games that you study, and you show undecidability of the optimization problem that I presented for this more restricted class of games, they're called linear system games, then you'd end up showing that there's a non-hyperlinear group. So in many cases, you can construct a group starting from the Bell inequality or the two-player game, but there are some conditions. Unfortunately, our proof doesn't satisfy these conditions, so we don't get a group out of it. It's possible, offline, I could say where in the proof do we lose track of this connection. In fact, it's present through most of the proof, and at some points, due to some arguments from complexity, actually, we lose the connection. So, but that's a natural direction to try to explore, which I think some people are exploring, I'm sure, but it's not obvious how to do it. Yeah, thanks.
There is an online question. The split property generically only holds for well-separated regions, but it may fail for space-like separated regions with a common boundary point. Do you think this could help in finding a QFT model?
Yeah, so you'd have to start with something like this. So what the question says is that if if you study regions that are well separated, then the split property is going to hold, and then the two models are going to be equivalent. So definitely don't go there. You're going to have to allow the regions to touch, but then, I'm out of my depth here. So then I don't know what you do next. I think if you just start with the axioms, like the most minimal, like Haag's axioms, I think, for algebraic QFT, then you can do it because these don't impose anything. But if you want to say, well, you want to write down a more specific model of what the algebra exactly is and have a thought that this is something that's kind of like physical, then I think in many cases, even if these regions touch, I think there's some other property of the algebra that makes it that you don't see a separation. But maybe the person who asked the question knows better than me, and I think it's, I don't really know.
Any other question?
So whenever Alice and Bob enter the scene, I get lost. Could you present these results without referring to Alice and Bob and their games? That's question one. And question two is, are there any sort of physics implications of this result? I mean, can I design experiments whose interpretation requires understanding your theorems?
Yeah, so for the first question, I wish. I know that Alice and Bob are, pet peeves of quantum information theorists and quantum cryptographers, and not every mathematical physicist. This is how I know how to show the result. I know how to think about constructing interesting Bell inequalities by thinking of them as games. Why do I want to think about them as games? Not because I like to play games, but because it gives me a way to use the tools of complexity theory that think of these games as constraint satisfaction problems. When I talk to mathematicians, they also, or maybe you're a mathematician, so you are a mathematician, I'm sure. They also don't like these games and the complexity theory, okay? They want to work just with algebras directly, maybe construct algebras that have certain properties. There are some kind of limiting arguments in the proof that involve things that are very close to Turing's proof that the halting problem is undecidable. And I don't know how to carry out these limiting arguments outside of the language of complexity theory, but I don't doubt that there ought to be a way to do it. So I'd encourage anyone to not read out, well, okay, to read our proof, but also to not read it and just, try to do it yourself. The second question is what I was, second question is there any physical relevance? I think there's extremely limited physical relevance, if any. I think of this more as a question in foundations, in complexity theory, in operator algebras, but not really in physics, even though Boris Tsirelson asked it. He was a mathematical physicist. I think the only relevance is, so this is what I was trying to get at by talking about quantum field theory. So in principle, it's possible that you could come up with a model in quantum field theory such that there's an experiment in that model that leads to certain predictions, such that these predictions could only be observed if really the most general formulation of quantum field theory is needed, meaning if really you, in some cases, cannot ascribe tensor product separations, even just from the point of view of producing the data that witnesses the experiment. Of course, by our result says that sort of computing, determining the setup for this experiment, what measurement should I make, etc., that's an uncomputable problem. So if you accept that, then it's going to be hard to come up with the experiment. So I think very limited relevance.
Another online question is about what about quantum mechanics for bosons and fermions that don't seem to have tensor product structure?
Okay, so I always get confused by this. No, but I think they do. So if you, David, can you answer this? So I think these systems are, I think maybe I shouldn't answer that question live because I'm not, I think it's not, okay, so someone, Bruno.
Well, if you separate the two pieces, it's equivalent, even if fermions are present, you can make the graded commutation a commutation, and then you get a tensor product structure under the same conditions as for.
Yeah, so I think that if you're in a non-relativistic setting and you have two different systems, they can be bosonless fermions, it doesn't matter, you're going to be able to model them using a tensor product. This is what you said, right?
Right.
Yeah. Thanks.
Okay. One last question maybe there.
Yeah, so just out of curiosity, it's an outsider to this field, relating to these different complexity classes. Is there actually an idea how to actually classify these classes? Because at least for me, it now looked as if it's just like historically, okay, people find there may be different complexity classes which people didn't thought of yet, but is there somehow an idea of an underlying principle how to classify these classes actually?
Yeah. It depends what you mean by classify, but that's the goal of complexity theory. So I mean, really basic way in which they're classified, I don't know if this is what you want, but it's just by showing inclusion diagrams. So you draw, this was my picture on the first slide, but maybe you don't remember. You draw each class as a set. It's the set of all problems, computational problems that lie in the class. And then you show that certain classes contain others or are not contained in others, etc. And then maybe a bit more broadly, you can try to classify them. There's different styles of complexity classes. There's time complexity, space complexity. There can be other resources that you try to measure in the definition of the class. You can also try to find more maybe high level or I don't know, structural principles about problems that would make them fit into maybe not one class, but one set of classes and things like that. So. People introduce these complexity classes just as a way to understand problems. Like everyone here every day is faced with some computational problems. Very simple things, how do I go from A to B, and harder things, how do I compute this expectation value and this model make a prediction. All these are computational problems. And the goal of complexity theory is just to identify features in computational problems that make them look similar, and then to prove that they're similar in formal sense. If you can solve this problem, then you can also solve that problem, etc. So,
yeah, great, thank you.
Okay, so let's thank Thomas again.
A brief announcement for the IMP General Assembly of this afternoon for the members. So on-site members can come to this room D at 4 o'clock. Online members should join remotely using the link that they received from the IMP officers. There is no link on the virtual platform for the General Assembly. Thanks.